Let's do a quick review of the basic states of matter. You have solids, which are basically any material that's under strong connections between the molecules, which basically allow the molecules to fluctuate or maybe even move a little bit, vibrate sideways, but the molecules don't really move much. And if you don't do so, either because they're under extreme pressure or they're because they are actually cold and not actually have a lot of kinetic energy, because the states of matter are basically representations of the way that the matter is acting because of the energy, the pressure, and other properties that you're actually changing because of the matter. So let's talk about some of those things. So again, solids are either compressed matter or cold matter that doesn't have a lot of thermal power. Notice, by the way, if you continue to implode that matter at higher pressure, you make the matter less free to actually move around. But if you actually warm up the matter, you actually make the matter tend to flow around more. So that's the conundrum. The more you increase the pressure, the more the matter hits each other, the more it warms up. So it becomes harder to pressurize it even more. So in terms of using pressure to change the states of matter, that's going to be limited by the temperature. But the same thing is true about temperature. As you increase the temperature, you create more pressure, which also then makes the things be more likely to actually remain solid. So there's this balance between pressure and temperature that exists in matter. And one of the early scientists, Lavoisier, was actually the first one to notice this relationship between pressure and temperature in the gases, for example. Now, a liquid would be a little more flexible. The bonds between the molecules would be very weak, and the particles would be allowed to flow or move around instead of just vibrate as they did in the solid. And then we're moving a lot faster. They have more kinetic energy or under less pressure. Now, once you get to the gas, the molecules are moving so fast that there's basically no attraction between the particles, and they're just chaotically moving around the medium. And they have a lot of kinetic energy, and that's why they're acting like a gas. Now, the level of organization of the system is going to be decreasing as you go up, while the temperature increases as you go towards the gas. So as you move towards the gas, temperature is increasing, but disorder is also increasing. And you can create the gaseous state by lowering the pressure. But remember, at higher temperatures, pressure will also actually increase in a confined space. Either way, now the solids are going to be transferred towards a gas through a process that we call sublimation. It is possible for matter to absorb enough energy to jump straight from solid to gas. It's also possible for matter to lose enough energy that will go straight from gas towards solid in a process that's called deposition. And so you see, this will be gaining energy, while deposition will be losing energy, going to a lower state of energy. Now, the same thing is true about freezing. When you go from liquid to solid, you're going to lose energy. Or condensation, when you go from gas to liquid. Now, when you go from solid to liquid, it's called melting, and from liquid to gas, it's called vaporization. Now, another thing that's interesting about matter is that in between these states, you have what's called phase transitions, or the actual event in which the liquid, for example, is becoming a gas. So during vaporization, the entire liquid is basically becoming a gas, and the temperature will never go higher than that temperature until the entire liquid has become gas, and then the temperature is allowed to actually go higher. And the same thing is true about when things are melting. Things melt at the melting point. After everything is melted, then it starts actually warming up beyond that. Now, you probably heard about the basic three states of matter: solid, liquid, and gas. But you may not have heard about some of the strange states of matter or matter phases, which we will be discussing in this video. Now, I'm just giving you an overview of these things. I'm not going to explain them in detail. And the only ones that I actually require you to understand is the idea of plasma and matter condensates. In other words, I want you to understand that when matter is super cooled or very, 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 very cold, it starts acting different from the solid that you think of. In fact, there's things like super solids or super fluids or Bose-Einstein condensate or fermionic condensates. Now, you don't actually need to know what those things are, but you need to know that there are other states of matter that occur when matter cools down to extreme extents and starts acting different from the actual solid. There's also other things you think are solid, like glass, plastic crystals, liquid crystals, which seem to be solid, but they're actually not really fitting the characteristics of a solid. And you also have high energy states like
the quark-gluon plasma, like gravitational singularities, degenerate matter under high pressure states, for example. And so there are other states or phases of matter which are not just the classic three states of matter. Now, there are a few that you actually need to understand what they are. And you need to know what plasma is. That's a special state that forms when gas ionizes. And if you deionize plasma, you go back to gas. Now, how do you go from actual gas to plasma? Now, look the way the gas looks here, and then look at the way the plasma looks there. The biggest difference is that instead of having the electrons orbiting the nucleus like a normal matter would, the plasma has free-flowing electrons. The electrons are flowing like crazy around each other, and they're not actually a part of an atomic structure. When we learn about the atom, we learn about these electrons that flow around the nucleus. But in plasma, all the atoms are ions. In other words, they are charged particles. You're going to have these positive nucleus flowing around and these negative leptons or electrons flowing around there. And so you have charged particles all in a jumbled mess. I call it a soup of fermions, and it's not actually assuming the Nuragel thing. What's happening there is that the particle got so much energy that the electrons are started spinning so fast that they actually take off from the atom. And that's how plasma looks like. By the way, you do not need heat to do this. It's possible to do it with heat, and that's how stars do it. They make plasma because it's so hot that the particles have so much electrical energy. But it's also possible to excite the electrons without necessarily heating them up. You've seen that thing that you touch and you get something that looks like lightning inside the ball. That's plasma. You can also create plasma in the microwave. I do it in class. And you can also have plasma TVs. You have plasma lights and all of these kinds of things. And so there's no necessarily to be hot in order to see plasma. You probably see it every day even though you don't notice. It's just whenever you ionize the gas. And you also need to have a general understanding what a matter condensate is. A condensate is basically going to be any time the matter is pushed in so much, so close together, or so cold that the entire particles that are in that matter will act like one big particle. They're still made of tiny little particles, which are individual little particles, but the matter will act like a unity. Almost as every single particle within that block of matter is acting in the same wave function. They're acting like a unit. You do something to one, all of them respond exactly the same way. And that's going to be important for superconductors because you can use that as a superconductor because the moment you do something to a corner, you actually almost instantly did to the opposite corner. So if you were able to do a cable like that, you could transfer information to that cable really, really quick. And that's be a really good application in scientific ways. And so that's why we want to know about that. And there's also the superheated states where matter starts acting like the way that we understand as individual particles get together to form atoms and things like that. On the contrary, it starts to break down and separate into its constituent parts. Now, other than that, the rest is a bonus. But watch it and see what you learn about it and see if you actually get interested on some of these things we're going to be talking about.